Hello APC Mechanics students, in Unit 3, Work, Energy and Power, Class 2, 3.1 Work, Part 2. Then Section 1, Work done by gravity. Now we're gonna investigate the work done by the previous forces that we have discussed in Unit 2. An object of mass m is displaced downward by vertical distance h. The pull of gravity Fg is downward, the displacement d is downward. Then the work done by the pull of gravity is given by the dot product between the pull of gravity and the displacement, and that would be Fg multiplied by h. And no need for a cosine because these two are parallel, and here we have a plus sign because they are acting in the same direction. And we know that the pull of gravity is given by mg, which means that the work done by the pull of gravity for a vertical downward displacement is positive, and it's given by mgh. Now if the same object is displaced upward by the same vertical distance h, the pull of gravity is downward, the displacement is up, then the work done by the pull of gravity is given by minus fgh. Why minus? Because now the vectors are anti-parallel. No need for a cosine because they are anti-parallel, and it would be minus mgh, which means that the work done by the pull of gravity for a vertical upward displacement is negative, and it's given by minus mgh. Now what about displacing the object up down along the ramp? An object of mass m is displaced downward along a ramp inclined by theta. The pull of gravity is down, the displacement d is down the ramp. Then the work done by the pull of gravity is Fg dot t, which is the projection of the pull of gravity along the displacement. Now that would be the angle theta. So if this is theta, this projection here would be cosine, and this projection here would be sine. So in this case it's given by sine theta. Then the projection of the pull of gravity along the displacement would be sine theta, and it's given by mgd sine theta. Here you should be very careful because d represents the displacement along the ramp. Okay, and this can be written as mgh. I will refer to it now, which means that the work done by the pull of gravity for a down displacement along a ramp is positive because we're moving down, and it's given by mgd sine theta, where d represents the displacement along the ramp. Now also this can be expressed as mgh because we know that if the work, we're saying that the work due to gravity downward is given by mgd sine theta, but we know that from the trigonometry of the triangle formed here, sine theta would be the opposite, which is h, over the hypotenuse, which is d. Then h would be given as d sine theta, so this expression can be replaced here by mgh. Then the work done along the downward motion of a ramp can be utilized in two forms, either mgh, where h represents the vertical distance, or mgd sine theta, where d represents the displacement along the ramp. And here, as you can notice, that independent of the path that we follow, the work done by the pull of gravity for any downward motion independent of the path, that would be mgh, which can be also written as mgh, where h in this case is the vertical height. Now if the same object is displaced upward along the ramp, the pull of gravity is down, the displacement is up, then the work done by the pull of gravity would be the projection of Fg along d. Now this would be the angle theta, so that would be the cosine and that would be the sine. But here in this case we need to utilize a minus sign because the pull of gravity is acting opposite to the displacement, and that would be minus mgd sine theta, which is minus mgh, where h would be the vertical height, which means that the work done by the pull of gravity for an up displacement along a ramp is negative, and it's given by minus mgd sine theta, where d is the displacement along the ramp. If h is the vertical height, now using the same trigonometry of the triangle, now sine theta would be h over d, which means that h is d sine theta, and this can be promoted to be h, and also can be written as minus mgh, where h is the vertical height. So in brief, whenever an object is being displaced down, the work done by the pull of gravity is positive and is given by mgh, which is the force, the pull of gravity mg times the vertical distance. It's being displaced up, that would be minus mgh. If it's being displaced down a ramp, that would be also mgh, where h is the vertical height, and it can be expressed as d sine theta, where d is the displacement along the ramp and theta is the angle of inclination. If it's displaced up the ramp, that would be minus mgh, where h is the vertical height, or minus mgd sine theta, where d is the displacement along the ramp and theta is the angle of inclination. Now section 2, work as area under a curve. So far we have seen that curves in general encodes information at the level of the slope, y-intercept, x-intercept. One important feature, as we have seen, is the area bounded by the curve. Consider a curve that shows the variation of f as function of displacement. Now what is the dimension of the area? The area would have the dimension of f multiplied by delta x, which is Newton's meters, and Newton's meters is the unit of work, which is basically joules, which means that the area under an f delta x curve has unit of joules, which represents work done by the given force f. Now work can be positive or negative, therefore area above the horizontal axis would represent positive work done on the system, and area below the horizontal axis would represent negative work done on the system. Now section 3, circular motion again. Consider a block attached to a string and rotating at a constant speed on a frictionless table. The forces acting on the block would be the pull of gravity down, the normal push up, and the tension in the string, which causes the centripetal motion. And this tension force should be equated by mv square over r, which is the quantity needed in order to maintain the circular motion. Then now we can talk about the work done by these three forces that are given by the work done by the pull of gravity, the work done by the normal push, and the work done by the tension. The work done by the normal push would be always 0. Now let's utilize here the displacement if the block is moving along the circle. Now the displacement would be tangent to the circle, and at this particular point would be represented like that. At this particular point it would be represented to the left. At this particular point it would be represented like that. At this particular point it will be represented like that. In this case we have that the work done by the pull of gravity is 0, the work done by the normal push is 0, and the work done by the tension is 0, because for any point along the circular motion the displacement would be perpendicular to the tension, the displacement would be perpendicular to the normal, and the displacement would be perpendicular to the pull of gravity, since each of the forces throughout the trajectory is perpendicular to the displacement d. However, this is not always true for circular motion. If the circular motion lies in a vertical plane, for example, the pull of gravity will make an angle different than 90 degrees with the displacement for different positions. If we're talking about vertical circle like this, and this is the string, and this bob here is performing circular motion, then we can say that the pull of gravity is down and the displacement would be tangent to the circle. In this case the problem is more complicated, and indeed the pull of gravity will make an angle with the displacement different than 90 degrees. However, here we're talking about horizontal circular motion. The work done by the pull of gravity, the tension, and the normal push would be exactly 0. And by that, the work done by the pull of gravity is not always necessarily 0. We have said that the work done by the normal push is always 0. The work done by frictional forces, if they are resisting motion, is always 0. And now for the remaining part of the video, we're gonna solve exercises. A student holds one end of a string in a fixed position. A ball of mass 0.2 kg attached to the other end of the string moves in a horizontal circle of radius 0.5 meters with a constant speed of 5 meters per second. How much work is done on the ball by the string during each revolution? This is a horizontal circle, and the correct choice would be A. So each work done by each force solely is 0. And this can be also understood as follows: because the speed is constant, then according to the work energy theorem, delta K is the work done by the external forces. No, here, sorry, they're asking only for the work done by the string, so we cannot use all the external forces. So we know that the string, the tension in the string will be always perpendicular to the displacement. For this reason, the work done by the tension, which is the string, would be 0. Now exercise 2, a weightlifter lifts a mass at a constant speed, so the weight is being lifted up. So the work done by the weightlifter would be the work done by gravity, which is basically mgh. Now here, why it is minus not plus? Because the weightlifter should perform work opposite to the work performed by the pull of gravity. The pull of gravity is doing a work which is minus mgh, then the weightlifter should add an energy equal to mgh, okay? Which is work is force times distance, which is mg multiplied by h. Now exercise 3, a box of mass 0.5 kg slides down a rough ramp with an initial speed of 2.0 meter per second. The ramp is inclined at an angle theta above the horizontal. The box slides a distance of 1.5 meters and comes to rest, so the final speed is 0. The energy dissipated would be the work done by the friction, and in order to calculate that, this can be utilized using the work energy theorem. Then let me say apply work energy theorem, and that would be the variation in the kinetic energy would equal to the external forces. Now kinetic energy final minus kinetic energy initial. What are the forces acting on the block? We would have the pull of gravity, we would have the normal push, and we would have the frictional forces. The normal push is always 0. Now the work done by gravity, if the box is moving down a ramp, that would be mgd sine theta, where d would represent the distance along the ramp. If they gave us the vertical distance, I would represent it as mgh. Now the kinetic final would be 0 because it comes to a rest, and that would be minus half mv square initial, and we're interested in determining the work done by the frictional forces, which represents the energy dissipated. Then the work done by the frictional forces would be minus half mv square initial minus mgd sine theta. That would be minus half, and the mass is 0.5, the speed is 2 to the power of 2, minus the mass, which is 0.5. We can use the g to be 9.8 and the distance to be 1.5 and theta to be 30 degrees. If you plug that on the calculator, you're gonna find minus 4.7 joules. If we're talking about energy dissipated, which is lost, we will say that, okay, the work done by friction is minus 4.7 joules, which means that the energy loss is 4.7 joules. Now exercise 4, a particle of mass m moves from point A to point D along the path shown in the figure. At each of the 4 labeled points, the net force on the particle is represented by a vector. How can one tell that the kinetic energy of the particle is increasing at point C? So we know that in order for the kinetic energy to increase, the work done should be positive. So in this case it's negative, or let me say it's negative, because the displacement is like this. That would be the displacement. The displacement here would be like this, and the displacement here would be like this, and the displacement here would be like this. Notice that for all the points A, B, and D, the displacement is opposite to the force, which means this is negative, 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 and in this one would be positive. Positive means that we're injecting energy to increase the speed. So the net force and the velocity are nearly parallel at point C. Remember that velocity gives you the direction of motion, which is basically the displacement vector. Now exercise 5, students set up an experiment with a small block on a ramp. The block of mass 0.3 kg is released from rest at the top of the curved ramp. The length of the ramp as measured along the curve is 0.3 meters and the height h is 1.5 meters as shown. There is negligible friction between the small block and the ramp. The students now move the block to a ramp that is identical to the first one except that it has a rough surface. Figure 1 shows the block as it's sliding down the ramp. Figure 2 shows a free body diagram for the block when it is at the moment shown in figure 1. Which of the following claims is supported by the figure? Friction does negative work on the block, because this is always the case. Now that would be, exercise 6. How does the work required to accelerate a particle from 10 meters per second to 20 meter per second compared to that 20 meter per second to 30 meter per second. We know that according to the work energy theorem, that the work done by the external forces is given by the variation in the kinetic energy, which is half mv square final minus half mv square initial, and now we can factor out half m, and that would be the final speed to the power 2 minus the initial speed to the power 2. Now we need to compare. First of all, let's calculate 30 square minus 20 square. 30 square minus 20 square would be equal to 500. Now, this is basically the initial configuration. The new configuration would be to accelerate it from 10 to 20, which means 20 square minus 10 square, and that would be 300. Comparing 300 to 500, which means it's easier, it requires less energy to accelerate it from 10 to 20 compared to 20 to 30, which means it is less, independent of the value of the mass, which is half m, because this is a common factor. Now exercise 7, the above graph shows the force F exerted on a 2 kg object as a function of the distance d that the object travels. Before we continue, let's utilize the curve. So this curve consists of straight lines, which means that we can make use of the x-intercept, y-intercept, the slope, and more over the area under the curve. This is an FD curve, which means the area would represent the work. The object is at rest at d is equal to 0 and travels a horizontal frictionless surface along the line of action of the force. The work done on the object by the force during the first 10 meters of the travel is most nearly. So we need to calculate the work done, not for the whole travel, but just for the 10 meters. So this is area A1, and that would be the area A2. The area A1 would be base times height over 2, which is basically 5 times 10 divided by 2, and that would be 25 joules. And the area A2 would be from 5 to 10, that's 5, length times width, which is 5 times 10, and that would be 50 joules, and the total work done would be 75 joules, 25 plus 50. Now the above graph shows the force F exerted on a 2 kg object as a function of the distance d that the object travels. The object starts at rest at d is equal to 0. So at this point the initial speed is 0. And travels on a horizontal frictionless surface along the line of action of the force. The kinetic energy of the 2 kg object when d equals to 20 meters is the same when d is most nearly. So here let's pay attention. They're asking, so okay, at d equals to 20 meters, we would have a final kinetic energy. Now how can we find this final kinetic energy? Then let's do it. And this can be done via the work energy theorem. So remember that you should write apply the work energy theorem, and the variation in the kinetic energy would be equal to the work done by the external forces. Now kinetic energy final minus kinetic energy initial would be the work done by the external forces. Now kinetic energy initial is 0 because we started from rest, so basically the final kinetic energy would be equal to the work done by the external forces. Now we're assuming here that we have a block, we have the pull of gravity, we have the normal push, and we have only a force F. Now this is not necessary to be horizontal, but I took it to be like that. That's fine, we don't have friction. Now let's calculate the value of K at d is equal to 20 meters. That would be equal to the work done by the external forces. Now previously we have determined this to be 25 joules, and this is 50 joules. Now what about this triangle here? Now here would be minus 50 joules. And what about these two triangles? No need to worry about them because one of them is positive and the other is negative, so they can be completely ignored. And that would be just 25, so let me complete it here, plus 50 plus a positive number plus a negative number that would cancel for this triangle, for these two triangles minus 50 joules. So basically it is equal to 25 joules. Then the kinetic energy at D is equal to 20 meters is given by 25 joules. Now let me again read the exercise and understand what they're asking for. They're telling us the kinetic energy of the 2 kg object when D equals to 20 meters is the same when D is most nearly. So if you think about it, energy is being added and extracted from the system. So basically that would be equal just to 5, because all of these, they cancel each other. So basically just when D is equal to 5 meters. Now exercise 9 as an exit ticket for today's video. The graph above shows the force of gravity on small mass as a function of its distance r from the center of the earth of radius re. So if you notice carefully, this is force as function of displacement, which means that the area under the curve would represent the work done by an external force, which is the force which is given. If the earth is assumed to have uniform density, the work done by the force of gravity when the small mass approaches earth from very far away, that would be infinity, and is placed at a circular orbit of radius r2, is best represented by the area under the curve just between r2 and infinity, which makes E to be the correct answer. And that's it for me in this video, guys. See you soon in a new one.